Hi dear students. So we have discussed about the moment of inertia. Now we have to see the two theorems which are regarding or related to this moment of inertia. The first one is the perpendicular axis and the next one the parallel axis. The two theorems are there. So the first one, the moment of inertia of a planar body. So here the condition is that the body that we are considering should be a planar or a plane. It should be in a plane. About an axis perpendicular to its plane is equal to the sum of its moment of inertia about two perpendicular axes concurrent with the perpendicular and lying in the plane of the body. So the perpendicular axis theorem is that the moment of inertia along one of the axes which is perpendicular to the plane of a planar body will be is equal to the sum of the moment of inertia along two axes which are lying on that body or on the plane of that body and which are perpendicular to each other, and as well these two axes should perpendicular to the axis that you are considering, that is which is perpendicular to the plane of the body. Okay, so suppose if you are considering the plane of the body, the body is lying in the x and y axis. Okay, the body is lying in the x and y axis. So the moment of inertia along the z axis will be Iz, that is Iz is equal to Ix plus Iy. Okay, so here Z, X and Y axes are perpendicular to each other, and the X and Y axis is lying upon the plane of the body. So the moment of inertia along the Z axis will be is equal to moment of inertia along the X axis plus the moment of inertia along the Y axis. Okay. Now come to the theorem of parallel axis. The theorem is that the moment of inertia of a body about any axis is equal to the sum of the moment of inertia of the body about parallel axis passing through its center of mass and the product of its mass and the square of the distance between two parallel axes. So you have to find out the moment of inertia of particular axis. You can consider any of the axes. It is not necessary that the axis should perpendicular to the plane. Any of the axes you are considering. And in this theorem, the parallel axis theorem, you can consider any kind of body. It is not necessary that the body should be a plane or a planar one. Then the moment of inertia along any of the axes will be is equal to the moment of inertia of the axis which is passing through the center of mass and which is parallel to this particular axis. Okay, that is Iz plus mass of the body m, and where a is actually the distance between these two parallel axes. One is the axis that you are going to find out the, for which we are going to find out the moment of inertia. Another one, it is the axis which is parallel to this axis and which is passing through the center of mass. So you have to find out the moment of inertia of the Z dash. So Iz dash is equal to this one. Iz dash is equal to this one is the Z dash. This one is the Z which is passing through the center of the mass, that is C. Okay. So here you have to find out the Iz dash. Iz dash is equal to Iz plus Iz this one. Iz plus m into the distance. Here in the above this theorem, the distance it is given as a. So Iz dash is equal to Iz plus the mass, sum of the in moment of inertia of the axis which is passing through the center of mass, and the product of the mass and the square of the distance between these two parallel axes. Okay. Now you have to find out the moment of inertia along the tangent of one circular ring. So where the distance between the mass of the ring it is m, the distance between the parallel axes it is r. So I tangent will be is equal to, that is moment of inertia along the tangent will be is equal to moment of inertia along the diameter plus mass into the square of the distance between these two axes. So along the diameter, in the case of the circular ring, the moment of inertia value it is mr square by 2, that we have already studied, plus m into r square. That is according to the parallel axis theorem, that is I tangent is equal to I diameter plus m into r square. So the value will be 3 by 2 mr square. So the value of the moment of inertia along the tangent will be is equal to 3 by 2 times mr square. Okay. Now the kinematics of rotational motion about a fixed axis. So the kinematics of a linear motion in one dimension with a uniform acceleration, that is the constant acceleration, we have already studied. So we comparing these things. Already we have seen the analog of linear velocity, that angular velocity omega will be instead of the linear velocity v, and as well angular velocity angular acceleration is represented by alpha, linear acceleration is a, and the displacement in terms of x we are representing in the case of linear motion, and here in this kind of angular motion the angular displacement, that is the angle, that is theta, we will take for the displacement. So comparing or with the help of this linear kinematic equations we will derive the angular kinematic or the kinematics of rotational motion we will derive. So first equation, we know that linear kinematic equation, the first equation is that v is equal to v0 plus at. V is the final velocity, v0 is the initial velocity, and a is the acceleration, and t is the time taken. So in the case of the angular motion, here the v will become omega, that is the final angular velocity omega, initial angular velocity omega 0, and alpha is the angular acceleration, and time t taken for this change or for the movement or the motion. So in the place of v is equal to v0 plus at, in the case of linear motion, the angular motion is having the equation as omega is equal to omega 0 plus alpha into t. Same way, the displacement, the second equation, that is x is equal to x0 plus v0 t plus half at square. So we have studied this one as s is equal to v0 t plus half at square. S is actually x minus x0. Final velocity, final position minus the initial position. The displacement s is equal to v0 t plus half at square. The same equation only. So x is equal to x0 plus v0 t plus half at square. Here instead of this x we are using the theta, the angular displacement. Theta is equal to theta 0 plus initial velocity v0, and here in the case of angular velocity that is omega 0 into t plus half into angular acceleration alpha into t square. Now the last equation, that is v square is equal to v0 square plus 2ax, where this x is actually x minus x0. Okay, the displacement. So here in this case of the angular motion, omega square will be is equal to omega 0 square plus 2 alpha into the displacement theta minus theta 0. Okay, so we are having the kinematic equation of the rotational motion as omega is equal to omega 0 plus alpha t, theta is equal to theta 0 plus omega 0 t plus half alpha t square, and the last one omega square is equal to omega 0 square plus 2 alpha into theta minus theta 0. Okay. Now one of the example question on the basis of this equation, we will discuss that one. The question is that the angular speed of a motor wheel is increased from 1200 rpm, where rpm is the rotation or the revolution per minute. rpm, it is revolution per minute, the number of rotations per minute, that is 1200. That was the initial, and final it is 3120 rotations per minute, and time taken for this transformation, this change, that is angular speed change, it is 16 seconds. Now we have to find what is its angular acceleration, assuming the acceleration to be uniform. So we are considering the acceleration, it is uniform, so uniform acceleration you have to consider, so we can use these equations. Then how many revolutions does the engine make during this time? So how many revolutions does the engine make? Now, so we can use the equation omega is equal to omega 0 plus alpha t here, and we have to find out the omega 0 and omega value. Here the omega 0 value it is given as 1200 rpm, rotations per minute, but we have to consider this one in the term of the unit, that in the unit as the radian per second. So you have to convert this rotation per minute to radian per second. So converting this rotation, one rotation means one complete circle. One complete circle in the sense in the radians it is 2 pi. So you have to multiply this 1200 into with the 2 pi. So 2 pi into 1200, and here rotations per minute it is given, we have to convert that into rotations per second. So divided by 60. Okay, divided it by 60, then you will get the rotations per second, revolutions per second you will get. So compare the revolution value you have to change into radian by multiplying it with the 2 pi, and the time changing towards the time you have to change into the seconds, for that you have to divide it by 60. So in radian per second, the 1200 rpm will be 40 pi radian per second. Okay, 40 pi radian per second, that is the initial velocity omega, initial angular velocity omega 0. Similarly, the final velocity value, that is 3120 rotations per minute. So that is 2 pi into 3120 divided by 60 radians per second, and that will be 104 pi radian per second. Now we have to find out the angular acceleration. It is asked to find out the question, the first question is that to find out the angular acceleration. So using this equation omega is equal to omega 0 plus alpha t, the alpha value will be omega minus omega 0 divided by t. Omega is 104 and omega 104 pi radian per second, and omega 0 it is 40 pi radian per second, and time taken it is 16 seconds. So alpha will be 104 minus 40 divided by 16, so value will be 4 pi radian per second square. So the angular acceleration value will be 4 pi radian per second square, that is the alpha value. So the now angular acceleration value it is 4 pi radian per second square. Now the next one it is the angular displacement in time t. So you have to find out the angular displacement, and with the help of that angular displacement we will find out the number of revolutions. So the angular displacement here it is theta is equal to, you can use that equation, that is angular displacement theta is equal to omega 0 t plus half alpha into t square. Now you are having omega 0, the time you are having, and as well the angular acceleration value also you are having. So Substituting these values in the equation, that is theta is equal to omega 0 t plus half alpha t square, you will get 40 pi. 40 pi is the omega 0 into t, that is 16. The half into alpha value, it is 4 pi radian per second, is 4 pi into t square, that is 16 square. So 640 pi plus 512 pi radian, that is the angular displacement, that is in actually radians. And radian it is, the unit is radian. So the question is that how many revolutions does the engine make during this time? So you have to find out the number of rotations. So if the angular displacement it is given in radians and you have to find out the number of rotations, then you have to divide the radian value with the 2 pi, then you will get the number of rotations. So 1152 divided by 2 pi, 52 pi divided by 2 pi will be 576, and the number of rotations will be 576. Okay, the number of revolutions will be 576. Okay, so study these equations, compare the angular kinematic equations with the linear kinematic equation, then it will be easy to remember. And once you go through the textbook and study everything thoroughly. Okay, thank you.